Okay, so symmetry. I'm sure a lot of us know what symmetry is, and we're going to look at some of the symmetry that we've looked at before. You may have seen this, or you just may, in general, know what symmetry is, but we're also going to look at a new type of symmetry that we may not be as familiar with, but overall, everything we look at today is pretty simple. Okay, so what is symmetry? Well, symmetry is basically the property of having an object flipped, rotated, or moved to map exactly onto itself. The one that we're most often familiar with is something being flipped onto itself. If you ever created like a Valentine's Day card, if you fold a piece of paper in half and then cut one half of the heart out of it and then unfold it, you'll get two congruent halves, and those two halves are symmetrical. And so that's the type of symmetry that we know. There's an implied congruence of sides and angles whenever things are symmetrical. So things are symmetrical because both of the halves are equal to each other. They're pretty much the same, and that's why we refer to them as symmetrical. If there is symmetry, then the angles and sides will always be congruent. So that's just a little bit about symmetry. So the type of symmetry that we know more often is actually called reflectional symmetry. And reflectional symmetry of a geometric figure is just the characteristic of a figure being able to map onto itself about a line of symmetry. So the kind of symmetry we know. The actual folded part, like if we were to fold this triangle in half, I would create two congruent halves, but the folded part is actually known as the line of symmetry, which I'm sure many of us know, but just in case, that is a line of symmetry. So reflectional symmetry is basically the type of symmetry that we've already seen. We have two types of lines of symmetry when it comes to reflectional symmetry. We have vertical symmetry and horizontal symmetry. Vertical symmetry just runs up and down, and horizontal symmetry runs left and right. And so some figures will have both horizontal and vertical symmetry. Some will just have only vertical, some will only have horizontal, but that's useful to know about the different types of symmetry that you might encounter. So reflectional symmetry. So what we're actually going to get into, and this may be the only new thing as far as reflectional symmetry, it's basically the numbers of lines of reflectional symmetry will vary from each geometric figure, right? Not every figure has the same lines of symmetry. Some have less, some have none, some have more than others. Well, a figure is actually said to have n-fold reflectional symmetry, where n is equal to the number of lines of symmetry. So basically, instead of saying, oh, that square has 4 lines of symmetry, what we'd actually say is that square has 4-fold reflectional symmetry, and that's kind of how we talk about it in geometry. So this square right here has 4 lines of symmetry. It has 1 here, 2, 3, 4. It has 4 lines of symmetry, and instead of saying that square has 4 lines of symmetry, I would just say that that square has 4-fold reflectional symmetry. Okay, and that goes for all the figures. So instead of this rectangle having 2 lines of symmetry, it will have 2-fold reflectional symmetry, and instead of this triangle having 3 reflectional symmetry or 3 lines of symmetry, it will have 3-fold reflectional symmetry. So when I just want to say n, which represents the number of lines of symmetry, fold reflectional symmetry. Okay. Any questions about this? Questions, concerns? Pretty straightforward. And so here's just some information about reflectional symmetry of trapezoids. Trapezoids tend to only have 1-fold reflectional symmetry, or absolutely none, because they can only really be mapped onto themselves about 1 line of symmetry, so 1-fold reflectional symmetry. Or they can have no reflectional symmetry like we see over here. The reason this has no reflectional symmetry is because those 2 halves are congruent. In order for it to be congruent, we would want to see it kind of exist a little bit more up here to be 2 congruent halves. So because those aren't 2 congruent halves, that would have no reflectional symmetry. All right, any questions about this? Okay, and so here is the really big, really unique thing about reflectional symmetry. It's basically talking about regular polygons, and a regular polygon is a polygon that has both equiangular and equilateral. So basically all the angles are the same and all the side lengths are the same. So that's what it means by equiangular and equilateral. Equiangular is all the sides, equiangular is all the angles, equal angle, and then equilateral is all the sides, equal sides. Well, the unique thing about regular polygons is that the number of reflectional symmetry is actually equal to the number of sides. So instead of me actually having to go about looking for all the different lines of symmetry of this triangle or of this hexagon, all I would have to do is count the number of sides, and the number of sides would be equal to the number of reflectional symmetry. So this triangle obviously has 1, 2, 3 sides, and because this is an equilateral triangle, that means all the angles and all the sides are equal to each other. And so because of that, I can automatically say that it has 3, where 3 is equal to the number of sides, 3-fold reflectional symmetry. Okay. The hexagon, on the other hand, again, instead of having to actually go about looking for each of the lines of symmetry, which may take a long time if I have more sides, there are some regular polygons that have like 100 equal sides, or instead of having to find all those different lines of symmetry, all you have to do is count the number of sides. So if I know that this hexagon has, oops, I keep doing that, has 6 equal sides, because it has 6 sides, then I can just automatically say, okay, then that hexagon has to have 6-fold reflectional symmetry. And again, we say fold reflectional symmetry to represent the lines of symmetry. Okay, so that's the unique thing about regular polygons, is the number of reflectional symmetry is basically equal to the number of sides. Okay, any questions here? Questions, concerns? Okay, and so now we're going to get into is rotational symmetry. You may not be super familiar with the rotational symmetry, but it's pretty straightforward. And so I'm going to show a video just to introduce it, and then we'll come back. So let me play this video, and then we'll come back.
Welcome to Moo Math, where we upload a new math video every day. In this math video definition, I would like to talk about rotational symmetry. Rotational symmetry is when an object is rotated around the center point a number of degrees and the object appears the same. The order of symmetry is the number of positions the object looks the same in a 360-degree rotation. This shape has an order of 3. This star has an order of 5. Thanks for watching. Moo Math uploads a new math video every day. Please subscribe and share.
All right, so that is basically rotational symmetry. Pretty straightforward, but just a little bit more of an understanding. Basically, what you're trying to do with rotational symmetry is you're trying to get it to map back onto itself. So for example, say I had this rectangle, and I wanted to rotate that rectangle 90 degrees. Well, as you can see there, it did not map back to where it originally was, where that gray bordered line is. I want it to map back to where it originally was. And so I'll rotate it again 180. And what you'll see is it does in fact map back. So that means I have at least one order of rotational symmetry. And then I'll try 270 degrees. Again, it doesn't map back, so that's not one of my orders of rotational symmetry. But I'll try again 360 degrees. And what you'll notice is it map back. So a rectangle actually has 2 orders of rotational symmetry. And we'll see why we call it order of rotational symmetry in a bit. Basically, that is as far as what rotational symmetry is. It's your ability to rotate something about a center point and get it to map back to where it originally was. How many times are you able to do that? Okay, let me go back, share my. Okay, So rotational symmetry. So the rotational symmetry of a geometric figure is the characterization of a figure to map onto itself through a center of rotation. So that's basically what we just discussed. The number of rotational symmetry that a figure has is actually called order of rotational symmetry. So the other one was called fold of reflectional symmetry. This one's order of rotational symmetry. So basically, if something has 4 rotational symmetries, then we would say it has 4 order of rotational symmetry. And that's just the way that we talk about it in geometry. And so instead of 2, it would have 2 order of rotational symmetry. And then instead of 3, it would have 3 order of rotational symmetry. So that's just a little bit of a different way that we reference rotational symmetry. All right, is there any questions about this so far? No? Okay. And so very similarly, here we have rotational symmetry of trapezoids. So this is asking what is the rotational chemistry for these 2 trapezoids. Well, the unique thing about trapezoids is they're kind of interesting in that the only instance in which you will have rotational symmetry or which the trapezoids will be able to map back onto themselves is when we have a full 360-degree rotation. And so that's the similarity you see here. In fact, every figure that you can think of has to have at least 1 order of rotational symmetry. So the minimum is 1 order rotational symmetry. And you might be asking why that is. And the reason is because we can basically turn any figure, whatever figure it is, around 360 degrees and get it to map back to where it originally was. And so that's the unique thing about rotational symmetry is that every figure, no matter what it is, even if it's these trapezoids, they have to have at least 1 order of rotational symmetry because you can basically rotate anything 360 degrees, okay? Any questions about this? Okay. And so what about regular polygons? Well, regular polygons is very similar in rotational symmetry as it is to reflectional symmetry. And that is that regular polygons with n equal sides will have n sides, which reference to n order of rotational symmetry. So basically, the number of rotational symmetry is equal to the number of sides, like we saw before. So here we have this equilateral triangle. This equilateral triangle is in fact a regular polygon. It has 1, 2, 3 sides. And so because we know it has 3 sides, we can say it has 3 order rotational symmetry. And so this applies for every regular polygon. And so again, if I had that hexagon I saw earlier, that has 6 sides, so it would have 6 order reflectional symmetry or rotational symmetry. So that's a unique thing that also applies to rotational symmetry. Another really unique thing that you can do here is that instead of having to actually go about rotating all these different figures to find all the different instances in which it will map back to itself, there's actually an equation you can use to identify all the instances in which that thing will map back to itself. So this is an example. So basically what you want to do is you want to use this equation right here, which is 360 over n, where n is equal to the number of sides. So I have 3 sides. So I go 360 over n. N is equal to the number of sides, so I'll input 3. And basically what this is going to tell me, it's going to tell me all the instances in which, or all the degrees in which I can rotate this triangle to get it to map back onto itself without me actually having to do that. So I do 360 divided by 3. That is 120. Okay? So what does that mean? Well, what you can actually do is take that 120 and multiply it by each of the sides. So I have 1 side, 2 sides. I have 3 sides in my triangle. And so because of that, I have 3 orders of rotational symmetry, and this is going to tell me what exactly those orders are. So 120 times 1, 120. 120 times 2, 240. 120 times 3, 360. And so basically that's all the instances in which I can rotate this equilateral triangle around to get it to map back onto itself. And so that's a really unique thing that we can do when it comes to rotational symmetry. And that's what you see here. You see all these different instances in which you can rotate this equilateral triangle to get mapped back onto itself. And if you were asked, okay, what's the smallest amount that it can map back onto itself? What is the smallest angle of rotational symmetry? Basically, it is what you divide it by, because that is equal to If you multiply that by 1, it's 120, and that's obviously your smallest angle out of your other 3 angles that we see here. Okay, so the smallest angle of rotational symmetry would be 120 in this instance. The largest, 360. Okay, any questions about this? And we'll look at a little bit more of an example. Okay, so here is another example. Here, how do we know? We know this is a regular polygon. Okay, how many orders of rotational symmetry does it have? Well, it has 1, 2, 3, 4, 5, 6. It has 6 sides, so it has 6 order of rotational symmetry. It is a regular polygon, 6 sides, 6 order of rotational symmetry. Now, how to identify all the instances in which I can rotate this to get it to map back onto itself? Well, again, we use this equation. N is equal to the number of sides, 6 is equal to 60. How do I find all the instances? Well, I just multiply by each of the sides. So 1, 2, 3, 4, 5, and 6. That gives me 60, 120, 180, 240, 300, and of course 360. Okay. And then again, if I'm asked for the smallest order of rotational symmetry, 60 would be the smallest out of all 3 of those. Okay. Any questions about this? Questions, concerns? Okay. And so lastly, say I'm given this figure and I'm asked to find, okay, what is the reflectional symmetry and the rotational symmetry of this figure? Well, it's being told to me that it is in fact a regular polygon. So I just have to count the sides. 1, 2, 3, 4, 5. So that means it has 5 folds. Reflectional symmetry, as well as 5 order rotational symmetry, because it is equal to the number of sides. And then what if I want to know all the instances in which I can rotate it? Well, 360 divided by 5. I'll do that for you. 360 divided by 5, 72. So 72 multiplied by each of the sides, so 72. 144, 216. So basically, I'm just multiplying 72 by each of the sides. 88, and then 360. So those are my 5 instances, 1, 2, 3, 4, 5, in which I can rotate this figure, this regular polygon, to get it to map back onto itself. Really cool. So what did we go over today? We went over reflectional symmetry, which is basically the symmetry that we know already, which is just something being able to map onto itself about a line of symmetry. Regular polygons that have n-fold reflectional symmetry, where n is equal to the number of sides. Rotational symmetry is the ability for something to map onto itself, but it has to do so about a center of rotation, so it to map back to where the bounds of it were every time you turn it. And like always, the regular polygons with n order of rotational symmetry, n is equal to the number of sides. So that's a really easy way to find the reflectional symmetry of a regular polygon and the rotational symmetry of a regular polygon. Right? Any questions about anything that we looked at today? Questions, concerns? All right. If there's no other questions, you guys may log off. I will see you guys on Monday and have a good weekend. Bye, guys.